as we start off with Unit 2 on linear motion and waves, Topic 1 is on linear motion and force. There are some basics that we need to get out of the way before we start launching into some of the more detailed stuff here. And the first thing that we need to look at is the idea of a vector. Now, in order to explain what a vector is, we first of all need to be aware of the fact that the study of physics is basically about measurements and quantities. So the study of physics requires quantifying measurements. So being able to state how big something is, or how fast or how far, whatever the case may be. And in quantifying measurements, we can group them into two different types. And the two types of quantities, hopefully you will have seen these before. This should just be a reiteration of what you already know. So the two types of quantities that we're looking at here, the first being scalar quantities. Now with scalar quantities, they only have magnitude. So we can only say how big it is. So some examples that we might have for scalar quantities are things like time. So we'd say how much time is passing. We could say distance, so how far something has travelled. And distance uses the symbol s. How far something is travelling, so speed, which uses the symbol v, or something like mass. So how much matter something contains, using the symbol m. Now they're just a sample, they're not, that's not an exhaustive list by any stretch, but we will make sure that we go through and talk about quantities that, if they're a scalar quantity, I'll make sure I point that out as we go through the next couple of years. The other type of quantity then, as the title there suggested, are vector quantities. Now vector quantities have magnitude and direction. So all measurements are going to have a magnitude associated with them, but a vector quantity also has a direction associated with it. So some examples of things that we could talk about with vectors are things like force, so how much force you place on something. Now the symbol that we're going to use for force is going to be F with an arrow over the top of it. So if there's a quantity that's a vector, we're going to use an arrow over the top. Another quantity that would be a vector is displacement. And you'll notice that with displacement, it also uses the letter S, but with the arrow over the top it indicates it's a vector. So distance is the scalar quantity, displacement is the corresponding vector quantity. So think of displacement as being a distance with direction. Another one would be velocity, so again similar to, ties in with speed. So velocity, you can think of it as being speed with direction. We'll go into that in a little bit more detail when we start to look more specifically at linear motion. I should also mention here that the notation for vectors can vary depending on which source you're looking at. So some other representations that you might see are F with a sort of a little squiggle underneath it. Another alternative would be to have a bold character. But if you're looking at that sort of representation, you can see there me writing it, it's a bit hard to write bold. So it's more sort of textbooks or online materials that would use the bold representation. Another way to represent it is represent a vector is to do it graphically. So like literally drawing an arrow to represent a vector. If that was the case, we would probably still usually write what the vector is beside it as well. So just be aware that there are some different representations that you might come across depending on the source you're using, so don't get locked into just one way of representing vectors. Another point that I want to make here as well, if we're looking at, so just another little note here, if we're only concerned with the magnitude of a vector, we don't usually, well, there's a couple of different ways that it could be represented. The way that we are going to do it, so to avoid confusion, we're going to represent it by using the notation of, so the vector itself would be, say, force again. We're going to use the absolute value brackets. The reason for that is that if we use just the symbol F, there can be a little bit of confusion. And what I mean by that, so in the case of force, it's not that big a deal. But if we're looking at, say, a velocity, and we're interested in its magnitude, we would usually represent it that way. The reason for that is because that's not the same necessarily as the speed. So the magnitude of the velocity and the speed can sometimes be slightly different, depending on the circumstance or the situation that we're dealing with. And in some cases, when we're talking speed, that might actually be the average speed. So I'll endeavour to make sure I always use the absolute value brackets when we're just looking at the magnitude of a vector. The next thing then, when we're looking at scalars and vectors, is when we need to do operations with them. So if we're adding or subtracting scalars, it's pretty straightforward. We've got two quantities there. We need to figure out what the sum is or what the difference is. So we can just literally add or subtract the magnitudes. So it's a fairly obvious point, but just wanted to lead in with that first of all. So as an example, let's say we have two masses that are being combined into one object, and one of the masses has a mass of 2.5 kilograms, and the second mass has a mass of 1.0 kilograms. Now, if we're looking, say, for the total mass, might represent that with an m with the subscript t for total. So that would be m1 plus m2, which is 2.5 plus 1.0, so fairly straightforward calculation to give us 3.5 kilograms. So nice and easy, nothing difficult. When adding or subtracting vectors, it's a little bit different. Let's actually start off first of all with adding vectors. The magnitude, and sorry, we're only going to start off with one dimension. We'll start looking at 2 dimensions in Year 12 or in Unit 3. With adding vectors in one dimension, the direction becomes, or not, it doesn't become important, the direction is important. And so rather than sort of try and write a whole heap of notes as to what that means, we're just going to look at an example. So let's say we had a displacement of 175 meters north. So we'll write that detail in. Notice that we actually have to write that direction as part of the measurement. S2 is 42 meters south. So if we think about this situation, we're looking for the final displacement, we're really just adding those two vectors together. So it's going to be S1 plus S2. Now, if we drew this graphically, we'd have our vector S1 starting off from our original point and then directed north 175 meters. If we're then going to add S2 to it, we're basically then going to start out where S1 finishes and then draw S2 on top of that. So that would be our vector S2. So when we add those two vectors together, our final answer is then that red vector, so that would be our final displacement SF. So in order to do that calculation, we now need to sort of somehow work the numbers in here. And so what we're going to do is actually use positives and negatives. So we're going to make north, we're going to let north be the positive direction. So that then means that the direction south becomes negative. So in our calculation over here, we would write 175, and to make it a bit clearer, we'll write that it's plus negative 42. Alternatively, you could think of this as being 175 metres, or plus 175 metres, and this as being negative 42 metres. So the direction of north and south is kind of built into the representation of the positive and negative. But usually when we write a vector, we should still state the direction fairly clearly. So that then will give us a value of 132 metres north. Let's say for some reason you knew what that final displacement was and you needed to know what the one of the original displacements were. That becomes a case of subtracting vectors. And in the case of subtracting vectors, we're not actually really going to subtract. The direction of the second vector will basically be reversed. And added to the first. So what I mean by that is, let's say that we had, so we knew that our first vector, so the first displacement was say 25 meters, and we knew that the final displacement was 11 meters. So in this case, we know the original, sorry, I should say that that's north. So 11 meters north and 25 meters north for those two vectors. So that means our S1 looks like that. And just to make it clear, our final vector is that one there, SF. So what we're trying to find now is this vector here, which would be S2. Now the calculation is still the same, so SF is equal to S1 plus S2, but what we're now trying to find is that vector S2. So S2 is equal to SF minus S1. So if we were going to do that calculation, we would consider now, so as we just wrote there, the direction of the second vector is going to be reversed. So what we're really looking at here is the opposite direction for S1. So if you think about S1 being equal to 25 meters north, then from here we can say that negative S1 would be 25 meters south. So basically this calculation now becomes SF. So if we represent it graphically, there's SF, and we're going to add to that negative S1. So that will mean that S2 is then that vector there. So it makes it a little bit easier. We've now got, we'll still have north is positive. So north is positive. So that shorthand notation there that I'm using, that's not a T, made it slightly too big. So north is being positive. So that means we would then have our final displacement is 11. Negative S1 would then be negative 25. And so we would then go 11 minus 25 to give us 14 meters south. I know that's a really straightforward example. There will be more complicated situations where we have those sorts of calculations. So we'll have a practice at a few of these sorts of calculations in class to make sure everyone's got it well and truly under control.